double angle, half angle, and reduction identities. Objectives: use double angle formulas to find exact values. Use double angle formulas to verify identities. Use reduction formulas to simplify an expression. Use half angle formulas to find exact values. Now, deriving the double angle formula for sine begins with the sum formula, sine of alpha plus beta, shown here. But I know that I can state that sine of 2 alpha is equal to the sine of alpha plus alpha. Now, replacing the beta in the rest of that formula, I have the sine of alpha times the cosine of alpha plus the cosine of alpha times the sine of alpha. And this means we have the sine of 2 alpha is 2 sine alpha cosine alpha. The formula for the cosine of 2 alpha can be found similarly. I know that the cosine of 2 alpha can be expressed as the cosine of alpha plus alpha. This is the cosine of alpha times the cosine of alpha minus the sine of alpha times the sine of alpha. So the cosine of 2 alpha is cosine squared alpha minus sine squared alpha. Concerning the cosine of 2 alpha identity, we can use the Pythagorean properties and expand the double angle formula for cosine and get 2 more variations of cosine of the double angle. Remember that the cosine squared of theta plus sine squared theta equals 1. This means that the cosine squared theta is 1 minus sine squared theta. So in this formula, we can replace the cosine squared theta with 1 minus sine squared theta, and we still have the minus sine squared theta there. So this is 1 minus 2 sine squared theta. The other way that we can expand the double angle formula is by using, again, the Pythagorean properties, but sine squared theta is equal to 1 minus cosine squared theta. So we rewrite this as cosine squared theta minus sine squared theta is 1 minus cosine squared theta, making sure to put the parentheses so you're subtracting both of those terms. We then get cosine squared theta minus 1 plus cosine squared theta. So this gives us 2 cosine squared theta minus 1. Similarly, to derive the double angle formula for tangent, replacing alpha and beta with theta in the sum formula gives us the tangent of 2 theta is equal to the tangent of theta plus theta, which is the tangent of theta plus the tangent of theta divided by 1 minus tangent theta tangent theta. Now, tangent theta plus tangent theta is 2 tangent theta. And on the denominator, it simplifies to 1 minus the tangent squared of theta. So here is the collection of all of the double angle formulas for sine, cosine, and tangent. Given the sine of alpha equals 5/8 with alpha in quadrant 1, find the cosine of 2 alpha. So I know that the cosine of 2 alpha is equal to 1 minus 2 sine squared alpha. I've chosen this version of the double angle for cosine because I know what the sine of alpha is, and this is the formula that only involves the sine. So this is 1 minus 2 times the sine of alpha is 5/8, and that is being squared. So I have 1 minus 2 times 25/64. That means I have 1 minus 50/64, which is 14/64. And this simplifies down to be 7/32. Verify the identities. Cosine 4 theta minus sine to the 4th theta equals the cosine of 2 theta. Here I can use factoring. This is going to be the cosine squared theta minus sine squared theta times the cosine squared theta plus sine squared theta. I know that the cosine squared theta minus sine squared theta is cosine of 2 theta, and cosine squared theta plus sine squared theta is just 1. So the cosine of 2 theta times 1 gives me the cosine of 2 theta. Cosine 2 theta times cosine theta is equal to cosine cubed theta minus cosine theta sine squared theta. In this instance, I'm going to work on the right and see if I can simplify it into the left. So the first thing I see is that I could factor out a cosine theta. That gives me a cosine squared theta minus sine squared theta. And I know that this is cosine theta times cosine 2 theta. That's the same as a cosine 2 theta times the cosine of theta. Use reduction formulas to simplify an expression. We can use 2 of the 3 double angle formulas for cosine to derive the reduction formulas for sine and cosine. First, let's start with cosine 2 theta equals 1 minus 2 sine squared theta and solve for sine squared theta. So first, let's go ahead and move the negative 2 sine squared theta so that it's on the left. We'll add 2 sine squared theta to both sides. And we'll subtract the cosine 2 theta from both sides. This gives me a 1 minus cosine of 2 theta on the right. Now to solve for sine squared theta, we simply divide both sides by 2. So the sine squared theta is equivalent to 1 minus cosine 2 theta all over 2. So you can see why they call this a reduction formula. We used to have a square, and now we can express that without an exponent. So we've reduced the power. Now let's take cosine 2 theta equals 2 cosine squared theta minus 1 and solve it for cosine squared theta. So the first thing that we could do is go ahead and add 1 to both sides. This gives me a cosine 2 theta plus 1 equals 2 cosine squared theta, and then simply divide by 2 so that we can get cosine squared theta by itself, and it equals cosine of 2 theta plus 1 all over 2. Again, we've reduced the power on the cosine squared theta, so we don't have an exponent here anymore. Now the last reduction formula is derived by writing tangent in terms of sine and cosine. So I know that tangent squared theta is equal to the sine squared theta over the cosine squared theta. But sine squared theta is 1 minus cosine 2 theta over 2, and that's divided by cosine squared theta, which is cosine 2 theta plus 1 divided by 2. Now to simplify this compound fraction, I'm going to multiply by 2 over 2. That gives me a 1 minus cosine 2 theta divided by cosine 2 theta plus 1. Here are the reduction formulas written all together here for you. Write an equivalent expression for cosine to the fourth x that does not involve any powers of sine or cosine greater than 1. I know that the cosine fourth x is equal to cosine squared of x times cosine squared of x. This is equal to 1 plus cosine 2x all over 2 times 1 plus cosine of 2x over 2. This is going to give me 1/4 times 1 plus 2 cosine 2x plus cosine squared 2x. Now I can go ahead and use the power reducing formula again. 1/4 times 1 plus 2 cosine 2x plus, remember the cosine squared 2x is going to be 1 plus cosine of double what we had before. It was a 2x, now it's a 4x over 2. This is 1/4 plus 1/2 cosine 2x plus 1/8 plus 1/8 cosine 4x. Then we can go ahead and collect like terms. I have 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x. Let's use the power reducing formulas to prove that 10 times cosine to the fourth x equals 15/4 plus 5 cosine of 2x plus 5/4 cosine of 4x. So let's go ahead and start. I know that I have 10 times cosine squared x times cosine squared x. That makes our 10 cosine fourth x. This is going to be 10 times 1 plus cosine 2x over 2 and 1 plus cosine 2x over 2. Now I can go ahead and make this 10/4 times 1 plus 2 cosine 2x plus cosine squared 2x. Now I still have an exponent of 2, so I'm going to work on that. 10/4 simplifies to 5/2, and this is going to be 1 plus 2 cosine 2x plus 1 plus cosine 4x over 2. Now I have 5/2 plus 5 cosine 2x plus 5/4 plus 5/4 cosine 4x. Collecting my like terms of 5/2 and 5/4, I'll have 15 fourths plus 5 cosine 2x plus 5 fourths cosine 4x. Now using half angle formulas to find exact values. The half angle formula for sine is derived as follows. Sine squared of theta is equal to 1 minus cosine 2 theta over 2. Well, I know sine squared of alpha over 2 would then be equal to 1 minus the cosine of 2 times alpha over 2, all divided by 2. This is now 1 minus cosine of alpha over 2. So, in order to solve for my sine of alpha over 2, I'm going to take the square root, and the sine of alpha over 2 will be plus or minus the square root of 1 minus cosine alpha over 2. And generally this formula is not, here we have the half angle formulas. The sine of alpha over 2 is plus minus the square root of 1 minus cosine alpha over 2. And the cosine of alpha over 2 is plus minus the square root of 1 plus the cosine alpha over 2. The tangent of alpha over 2 is equal to plus or minus the square root of 1 minus cosine alpha over 1 plus cosine alpha. It could also be expressed as sine alpha over 1 plus cosine alpha, or as 1 minus cosine alpha over the sine. Given that tangent alpha equals 8/15 and alpha lies in quadrant 3, find the exact value of the following. Sine of alpha over 2. So first, let's go ahead and make a triangle. We know that we're in the third quadrant, so this is the position of our right triangle. And here is alpha. If the tangent of alpha is 8/15, that means that this is 8 and this is 15. The Pythagorean theorem is going to show us that that hypotenuse is 17. And if I'm in the third quadrant, I know that the 15 is negative and the 8 is also negative. So I'm going to go ahead and use the formula plus or minus square root 1 minus cosine alpha over 2. Now I need to decide here if this is going to be a plus or a minus. So let's look at it this way. My angle of alpha is in quadrant 3. That means it's somewhere between 180 degrees and 270 degrees. So if we're trying to find the sine of half of that, where will half of the angle of alpha go? Well, half of 180 degrees is 90 degrees. Half of 270 is 135. So the half angle is going to live somewhere here in the second quadrant. And I know in that quadrant that my cosine is negative, the sine is positive. So positive is what I'm going to go with because we're talking about the sine of this alpha over 2. Now I can go ahead and find my values and put into the formula. This is the positive square root of 1 minus the cosine of alpha is adjacent over hypotenuse. So that's going to be a negative 15/17. That's all over 2. So now I need to take care of the compound fraction inside the radical. I'm going to multiply inside by 17/17, which is another form of 1. Then I'll have 17 plus 15 over 34. This is the square root of 32 over 34, which is the square root of 16 over 17, and that gives me 4 over the square root of 17. I have one last step to go ahead and rationalize the denominator. So I have 4 square roots of 17 over 17. Now, given the same information, let's find the tangent of alpha over 2. I'm going to use this version of the formula, sine of alpha over 1 plus cosine alpha. So sine of alpha is going to be opposite over hypotenuse. That's a negative 8/17 divided by 1 plus the cosine of alpha is adjacent over hypotenuse. So that's a negative 15/17. That's going to change that sign to a minus. And now I'm going to multiply top and bottom by 17 so that I can clear the compound fraction. I get a negative 8 on top. Alpha. On the bottom I get a 17 minus 15. So a negative 8 divided by 2 is negative 4. Given that sine alpha equals negative 4/5 and alpha lies in quadrant 4, find the exact value of cosine alpha over 2. So let's go ahead and draw a triangle. We're here in quadrant 4, so my hypotenuse is going this way from the origin, and I have this alpha is my angle here. I know the sine of alpha is opposite over hypotenuse, and this side will be 3 using the Pythagorean theorem. I know in the fourth quadrant that my sign here is going to be a negative. So now we're ready. Go ahead and decide what formula to use. Of course, the half angle identity for cosine. That's going to be plus or minus the square root of 1 plus cosine alpha, all divided by 2 here, all inside the square root. I still need to decide whether I'm going to use a positive or a negative here. Now let's see what sign we should choose. We're looking here. Alpha lives in quadrant 4, so it's going to be somewhere here between 270 degrees and 360 degrees. If we're looking at half of that, then we're going to be somewhere between 135 degrees and 180 degrees, somewhere in between here. So we'll be in quadrant 2, and in quadrant 2 I know that my cosine is negative. So I'm going to use the negative formula. Here I'm going to go ahead and start. I've got the cosine of alpha. Cosine is going to be 3/5. That's over 2. And now it's just simplification from here. I'm going to multiply by 5 over 5 inside there so that we can go ahead and clear the compound fraction. Now I have a negative square root of 8 over 10, which is negative square root of 4 over 5, and that is a negative 2 over square root of 5. And if we need a rationalized denominator, we can go ahead and multiply by the square root of 5 over the square root of 5. That'll give us negative 2 square roots of 5 over 5.